Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. This video is about higher order partial derivatives and the Hessian matrix. So, in an earlier video, we studied the notion of critical points for multivariable functions. So, what that meant was that you take the function f, so this is a scalar valued multivariable function, and then you find its gradient and then you set it to 0. And you compute all those points for which those equations are satisfied, which means that the gradient at that point is 0. Or the other thing that can happen is that one or more partial derivatives are undefined. So, you collect together all those points and those are called the critical points of f. And the reason we were interested in studying these was that the local extrema, meaning local maxima or local minima, are all critical points. So, they satisfy that the gradient is 0 or maybe some partial is not defined. So, they must satisfy one of these, and the intuition there was that the tangent plane is parallel to the xy plane, or in general the x1, x2, xn hyperplane. In one variable calculus, we have studied that there is a second order test, meaning a test using the second derivative, and that allows us to classify which of these critical points are local maxima, local minima or saddle points, and sometimes it can fail also. So, we would like an analog of such a test for the multivariable case, and in order to do that, we will first study the notion of higher order partial derivatives and the Hessian matrix. Okay. So, let us recall what are partial derivatives first. Suppose f of x1, x2, xn is a scalar valued multivariable function defined on a domain D in Rn. The partial derivative of f with respect to the variable xi is the function denoted by f subscript xi or del f del xi, and it is defined by taking the limit as h tends to 0, f of x tilde plus h times ei. What is ei? Ei is the ith unit vector in Rn, minus f of x tilde divided by h. So, this is the definition of the partial derivative function of f with respect to the ith variable xi, and its domain, it need not always, this limit need not always it need not always exist, and so the domain of this function, the partial derivative, is all those points within D where this limit does exist. And what does the partial derivative do? The partial derivative at a point A measures the rate of change of the function in the direction of the standard basis vector ei at the point A tilde. So, or equivalently with respect to the variable xi, meaning it treats the function as a function of only xi. So, you restrict to that line parallel to the xi axis passing through A tilde, and restrict your function to that line, and then ask what is the, how is the function changing, what is the rate of change of that function. That is exactly what the ith partial derivative does. Okay. So, now the partial derivative is a function, and so you can say what is the partial derivative of that function. The partial derivative is a scalar valued multivariable function, and we can very well ask what is the partial derivative of that function, and that is exactly what are second order partial derivatives for f x y. So, if f of x y is a function defined on the domain D in R2, then the second order partial derivatives of f are the partial derivatives of the partial derivatives. So, you take partial derivatives and then you again take partial derivatives. So, just for the sake of simplicity, the notations are either f subscript xx or del squared f del x squared. So, note this strange thing that the notation here is del squared f del x squared and not del squared f del squared x. So, this is for something that will come ahead. The other possibility is that you have f y y, which is also del squared f del y squared, and the third possibility is that you have f x y, which is the same as del squared f del y del x, or and the fourth possibility is f y x, which is del squared f del x del y. So, what do these mean? So, f x x means you consider the partial derivative f with respect to x of f with respect to x, and then take the partial derivative of that function again with respect to x, right. So, f subscript x again subscript x, or the other way of writing this is del x of the function del f del x. So, del f del x is the function, the partial with respect to x, and then you take the partial again with respect to x. Similarly, if you have f y y, what that means is you take partial with respect to y and then again take partial with respect to y. Equivalently, you could write it as del y of del f del y. What is f x y? So, this is where you first take the partial with respect to x and then take the partial with respect to y of that function, which is the same as saying you take del y of del f del x, and then here this is f y subscript x, and this is del x of del f del y. So, now just notice one small thing. This is a it's fairly obvious, but sometimes students make mistakes with this. In the notation, when you do f x y, so here the order is first differentiate with respect to x, then take partial with respect to y. Okay. But when you write it like this, it gets kind of flipped over, right. So, you have to remember that this means first take partial with respect to x and then take partial with respect to y. So, because of the notation, I mean on the notation on the right is sort of saying you take del of something, right, and that is why it is written like this, whereas on the left it's x is coming on the right, the variables are coming on the right, that is why you write it like this. So, you have to just remember that when you go between these two, whatever is written here gets written in the opposite order towards the left. So, the subscript notation gets written towards the right, the del notation gets written towards the left. This is what you should remember, because this is the common source of errors. Now, it would be of course convenient if we could flip these as we want, like if we have f x y and f y x, then we can interchange them. That would be very convenient, and indeed we will soon see a theorem that says that if your function is nice, meaning under some hypothesis, indeed that does happen. Let us start with some examples. So, let us compute all the second order partial derivatives of these functions. So, first what are the first order partial derivatives? So, del f del x, so we have actually computed these before, is 1, del f del y is 1, and so del squared del x squared is the partial of the function del f del x, which is 1. So, the partial of that is 0 because it is a constant. Then del squared f del y squared is similarly 0. In fact, all these functions are 0, right. Del squared f del x del y is also 0, and del squared f del y del x is also 0. And indeed, do notice that here these two are equal. So, at least for easy functions, it may happen that these two are often equal. So, it does not matter in which order you do your partial differentiation, the answer will be the same. Let us see if that holds for this as well. So, you have f of x y sine of x y, we have again computed the gradient here. So, we know what the partial derivatives look like. So, this is y times cosine of x y and x times cosine of x y. Now, let us look at the higher order partial derivatives. So, if you have del squared f del x squared, that means you have to differentiate y times cosine x y with respect to x. Now, y is a constant, so it will come out. So, you are just differentiating cosine of x y. So, this is y times minus sine of x y times y, right. So, this is minus y squared sine of x y. Now, by symmetry or by doing it, you can see that del squared f del y squared is also minus x squared times sin x y. So, I will suggest you check this. So, this leaves us with the mixed partial derivatives. So, del x del y and del squared f del y del x. So, for del squared f del x del y, we first differentiate with respect to y. So, that gives us x cosine x y and then differentiate with respect to x. So, this is your product rule. So, let us differentiate x first, that is 1. So, 1 times cosine of x y and then hold x and differentiate cosine of x y. So, that gives us y times minus y times sine of x y. So, what this gives us is cosine of x y minus x y times sine of x y. So, that is what it gives us. Okay. And then by symmetry or by computing it, maybe we can compute it. So, this is again 1 times cosine of x y. So, I am now differentiating y times cosine x y with respect to y. So, 1 times cosine of x y plus y times minus x sine of x y, right. So, which gives us cosine of x y minus x times minus x y times sine of x y. And again you can see that these two are indeed equal. So, it seems that the mixed partials are indeed often equal. Maybe I should have mentioned in the previous slide that these are called the mixed partials, the mixed partial derivatives. Yeah. Okay. So, as I was saying, the mixed partial derivatives, at least in these examples, seem to be equal, and indeed we have a very nice theorem called Clairaut's theorem about the mixed partials. So, it says the following. So, suppose f of x y is a function defined on a domain D in R2 containing a point A and an open ball around it. If the second order mixed partial derivatives f x y and f y x are continuous in an open ball around A, then they are equal at A. So, what do we need to check? That these mixed partial derivatives are continuous in an open ball around A. Now, in our previous examples, they were all very nice functions. So, continuity was not at all a problem, and from there we could as a result apply Clairaut's theorem, and we saw that they are equal, although we actually computed them, but we could have directly concluded it from Clairaut's theorem. Okay. So, let us see an example where we will try to compute all these and see that the hypothesis is indeed necessary. So, let us compute what are the partial derivatives. So, first of all, what is del f del x and del f del y at 0 0. So, del f del x at 0 0 is limit h tends to 0 f of 0 plus h comma 0 minus f of 0 comma 0 divided by h. So, f of 0 plus h, that is f of h comma 0. So, that is again 0. So, this is 0 minus 0 by h, but h tends to 0, and so this is going to be 0. By the same argument, the partial for y is also 0. So, we know that these two are 0. Of course, we have to compute now the partial derivatives at the other points as well. So, so now let us do that. So, what is del f del x at x y, where x y is not equal to 0 0. So, if x y is not equal to 0 0, then this is a rational function and the denominator is non-zero. So, I can apply my u by v rule. So, if we do that, let us see what we get. So, this is x squared plus y squared times the derivative of the numerator. So, that gives us y times x squared minus y squared plus x y times 2x minus xy times x squared minus y squared times 2x divided by x squared plus y squared squared. So, now if we simplify this, and I will not spend time on doing this since it is a direct simplification, what we are going to get is something like minus y to the power 5 plus x to the 4 times y plus 4x square y cube divided by x square plus y squared squared, and this is if of course x y is not equal to 0. Okay, and you can do the same thing for del f del y, and if we do that, what you will get is again you use the u by v rule and go through the expressions. You will get exactly the same thing, except that now the x term, the highest x term comes with a positive sign, and the lower ones come with a negative sign. So, x cube y squared divided by x square plus y square squared. So, it's kind of symmetric, except that there is this gap between the plus and the minus, and that gap is exactly what is going to cause the second order partials to not work out properly. So, this is what it is, and now let's compute what is the second order partial mixed partials for at 0 0. So, at 0 0 I want to compute what is del squared f del x del y 0 0. So, what does this mean? This means I have to compute limit h tends to 0 the partial of y at so this is with respect to h. So, h comma 0 minus del f del x at 0 0 divided by h. Okay, so what is the partial derivative at h comma 0? This is, so limit h to tends to 0, h to the power 5 minus everything else is 0 because the y coordinate is 0, and then divided by, that is the numerator, and then divided by h squared plus 0 squared squared, which is h to the power 4. So, we will simplify this in a minute. What is the partial of x at 0 0 that we have computed, that is 0, and then divided by h. So, if we do this, this is h to the h minus 0 by h limit h tends to 0, which is 1. Now, let us compute del squared f del y del x at 0 0. So, this is limit h tends to 0 del f del x at 0 comma h minus del f del x at 0 comma 0. I see in the previous one I have made a typo. This should have been del f del y, but it is the same. The answer does not change as such. Divided by h, and now we can again do the same thing. So, what is del f del x at 0 comma h? So, we have found out here that it is minus h to the power 5, and all the other terms do not contribute because there is a x in there, and the x we have to substitute is 0. So, minus h to the power 5, and then the denominator is 0 squared plus h squared squared minus 0 divided by h, and limit as h tends to 0, and you can see now this is minus 1, and so these do not match. So, these do not match. Okay. So, what was the problem? The problem was that these mixed partials are actually not continuous. So, for that you will have to actually evaluate what they are and check what happens. So, the hypothesis in Clairaut's theorem is important, and without that it may not happen that the mixed partials are indeed equal. So, for whatever is next, we will assume that the hypothesis of Clairaut's theorem holds, because we want that to hold in order to get whatever the second order partials are useful for. Fine. So, we have done second order partial derivatives for f x y. Now, let us talk about second order partials for f x 1 x 2 x n. So, if f x 1 x 2 x n is a function defined on the domain D in R n, then the second order partial derivatives are defined analogously as the partial derivatives of the partial derivatives. So, here there are for the in this 2 case there were 4 second order partial derivatives. So, for the general case there are going to be n squared second order partial derivatives. So, they are given by f x I x I or del squared f x I x I. So, what this means is you take f with respect to x I and again with respect to x I, or the same thing del x I of del f del x I, right. This is when I is equal to j. If I is not equal to j, or meaning this is a general situation, then this is f x I and then you take the partial with of x j of that, which is the same as saying you take del x j of del f del x I. So, again important point is to notice here how here it is written on the right, and so it goes the order is from left to right. Here it is written towards the left, and so the order is from right to left. Okay, that is the only thing you have to recall, remember as far as notation is concerned. And the other difference, meaning why did I write it differently? See, here the notations are same, f x I x I, here x I x j. So, it does not matter if I and j are different or I and j are the same. But when you write it in terms of this del notation, the del x I becomes del x I squared. This is just convention, there is no reason for this notation other than convention. Fine, let us do this example. If x y is x y plus y z plus z x, let us first compute the partial. So, del f del x is y plus z. Again we have done this example before, meaning the partials, first order partials before. This is x plus z or z plus x, and del f del z is x plus y. And so, if I want the second order partials, I differentiate these. So, del squared del x squared is 0, del squared del x del y del x is, so you take the function y plus z and differentiate with respect to y. So, this is 1, del squared del f del z del x is 1, and I think you can see the general pattern emerging. So, I will write it as del squared del y squared is 0, del squared f del z squared is 0, and then del squared f del z del y, this is the partial of the function del f del y, which is x plus z. So, partial of x plus z with respect to z, that is 1. And again if we know that the partials are, the second order partials are nice, then the mixed partials are actually, the order does not matter. So, from Clairaut's theorem or an equivalent version of the theorem in n dimensions, you can check that del squared f del x del y is also equal to 1, which is also del squared f del y del z, which is 1, and then del squared f del maybe I want a del x here, and then del y del z, all these are 1. Okay. So, you can check this directly from the expressions for del f, the first order partials, or you can use the fact that Clairaut's theorem applies. Okay. So, I will make that as a comment in this slide. So, before which let us define the higher order partial derivatives. So, you can keep repeating this process. So, you have the second order partials, you can take the third order partials, fourth order partials, right. So, for one variable functions, you can differentiate as many times as you want, provided the derivative exists. So, the same thing can be done for partial derivatives. You can take partial derivatives as many times as you want, and that is exactly what higher order partial derivatives do. So, if f x1 x2 xn is a function defined in the domain D in Rn, then the higher order partial derivatives of f are defined analogously by taking successive partial derivatives. So, the general notation, so if you take the kth order partial derivative, the notations are f xi1, xi2, xik, which means you take the partial with respect to xi1, then you take the partial with respect to xi2, then you take the partial with respect to xi3 and all the way up to xik. This is what it means. And you can write the same thing, except remember our usual thing about the shift in the order. So, this is exactly the same as taking del del xi of xik of del del xi k minus 1 of del del xik minus 2 of all the way up to del f del xi1, and then plenty of brackets, however many there are. Okay. So, I hope the idea is clear. It's exactly the same thing. Of course, once again one should point out that there is no guarantee that this higher order partial derivative exists, the same way as there is no guarantee that the first order partial derivative exists. So, there will be some points where it exists, some points it may not exist, and so the domain of this function is whichever points it exists on. Okay. And an appropriately modified statement of Clairaut's theorem holds. What that means is, if suppose you take the kth order partial derivatives, then if all the if this guy is continuous and so is in a neighborhood, and so is any you take this denominator in some other order, if that kth order partial is also continuous in some neighborhood, then they are going to match at the point at any point in that neighborhood. Okay. So, in general what you can say is, under suitable hypothesis, you can shift the orders without any problem. So, if I do xi1, xi2, xik, that is the same as doing it in some other order, x ij1, x ij2, x ijk, right. So, some confusing combinatorics may be, but all I am saying is you change the order of one through k. Instead of x1, x2, x3, you could have x2, x3, x1, and that is allowed under suitable hypothesis. Finally, let us talk about the Hessian matrix, which is really what all this is going to be used for. So, the Hessian matrix is the following. If you have a function of n variables defined on domain D in Rn, then the Hessian matrix of f is defined as this complicated looking n by n matrix. So, remember that you had n squared second order partial derivatives. So, you place them in a matrix. So, the first row is you take you take your gradient vector, and then you take the partials with respect to x1 of each component of that gradient vector. So, del squared f del x1 squared, del squared f del x1 del x2, del squared f del x1 xj. So, this is the jth column, del squared f del x1 del xn, that is the last column. And then for the second row you take del x2 of the gradient vector. So, del f del squared f del x2 del x1, del squared f del x2 del x2, then del squared f del x2 del xj, del squared f del x2 del xn, and then in general this is the ith row. So, the important part is you have to remember what happens for the ijth entry, right. That is how you describe any matrix, by saying what happens for the ijth entry. So, the ijth entry is given by taking del squared f del xi del xj. This is what you should remember. So, that is what is happening here. Okay. So, this is the Hessian matrix, and this is somehow going to come in, this is somehow going to be useful when we talk about the second derivative test, whatever. So, the analog of the second derivative test when we classify critical points. Fine, let us do a couple of examples. So, for this example x plus y, we saw that the second order partials are actually all 0. So, the Hessian here is 0 0 0 0. So, this was a relatively complicated Hessian sin x y. So, it's a 2 by 2 because you have two variables, and the terms here are so this is I think minus y squared sin x y minus x squared sin x y, and then this was a cosine of x y minus x y times sin of x y. Then this was cosine of x y minus x y times sin of x y. So, these terms typically match. So, often for the Hessian matrix these terms will match. And then let us do this one. This one was again a rather easy matrix. Now, this is a 3 by 3 matrix. Why 3? Because there are 3 variables. So, what was this matrix? This was 0 1 1, 1 0 1 and 1 1 0. Yeah, the kind of matrices we found in linear algebra were somewhat useful, and indeed we will have some use of linear algebra when we study the Hessian matrix in the context of the classification of critical points. Thank you.